Listening practice, 3D printer introduction. The construction industry stands at a pivotal crossroads. Traditional methods, burdened by rising costs, labor shortages, and environmental concerns, increasingly struggle to meet the demands of rapid urbanization and sustainable development. Enter 3D printing, a disruptive technology poised to redefine how we build. By layering materials with precision, 3D printing offers unprecedented speed, cost efficiency, and design freedom, transforming everything from emergency housing to intricate architectural masterpieces. This book, 3D Printing of Construction Materials for Rapid and Cost-Effective Building, explores the convergence of innovation and practicality. From the cobblestone streets of ancient Rome to the robotic arms of modern fabrication labs, we trace the evolution of construction technologies, underscoring why 3D printing is not merely an alternative but a necessity. You'll delve into the science of printable concrete, geopolymers, and recycled composites, uncover the mechanics of extrusion and powder bed systems, and witness how AI-driven robotics are erecting structures once deemed impossible. Structured into 7 comprehensive parts, this book balances technical rigor with real-world relevance. Whether you're an engineer seeking material insights, an architect pushing design boundaries, or a policymaker crafting forward-thinking regulations, these pages offer a roadmap to harnessing 3D printing's potential. As housing crises escalate and climate goals tighten, this technology emerges as a beacon of hope, a tool to build faster, smarter, and greener. Chapter 1, The Evolution of Construction Technologies. Introduction. From the mud-brick ziggurats of Mesopotamia to the steel-framed skyscrapers of the modern era, humanity's quest to build has shaped civilizations, economies, and landscapes. For millennia, construction methods evolved incrementally. Stone gave way to timber, timber to concrete, and manual labor to mechanized tools. Yet, despite these advancements, the industry remains tethered to practices riddled with inefficiencies, slow timelines, soaring costs, and environmental tolls. Today, as urbanization accelerates and climate crises escalate, the limitations of traditional construction have become impossible to ignore. Labor shortages, material waste, and rigid design constraints demand a paradigm shift, one that 3D printing promises to deliver. This chapter traces the arc of construction's evolution, examines the systemic challenges of conventional methods, and introduces 3D printing as a transformative force poised to redefine how we build. Conclusion. The history of construction is a testament to human ingenuity, yet its legacy is also one of stagnation. While innovations like reinforced concrete and prefabrication marked leaps forward, they failed to address core inefficiencies rooted in labor dependency, waste generation, and inflexible design. Traditional practices, now strained by global housing shortages and sustainability mandates, reveal an industry at a crossroads. Enter 3D printing, a technology that transcends incremental progress, offering precision, speed, and material efficiency unmatched by conventional methods. By layering materials with robotic accuracy, it not only mitigates long-standing challenges but unlocks possibilities for architectural creativity and equitable access to shelter. As we stand on the brink of this new era, 3D printing emerges not as a mere tool, but as a catalyst for reimagining construction itself, a bridge from the pyramids of the past to the sustainable, scalable cities of tomorrow. This introduction and conclusion frame Chapter 1 by contextualizing 3D printing within the broader narrative of construction history, underscoring its potential to resolve enduring challenges while inspiring readers to envision a redefined future. Chapter 2, Fundamentals of 3D Printing. Introduction. At the heart of the construction revolution lies additive manufacturing, a process that constructs objects layer by layer, in stark contrast to traditional subtractive methods that carve away material. This chapter demystifies the core principles of 3D printing, beginning with an overview of additive manufacturing technologies and their evolution from prototyping tools to industrial game changers. We explore the diverse techniques reshaping construction, including extrusion-based systems that deposit concrete like digital mortar and powder bed fusion methods binding materials with precision. Each technology brings unique advantages, from intricate geometries to rapid production, but all share a common promise: transforming design freedom into tangible structures. By examining these processes and their benefits, cost efficiency, waste reduction, and scalability, we lay the groundwork for understanding how 3D printing transcends conventional building limitations. Conclusion: the fundamentals of 3D printing reveal a technology as versatile as it is revolutionary. Extrusion-based methods, powder bed fusion, and other additive techniques each offer distinct pathways to reimagining construction, whether through robotic precision or resource efficiency. The benefits are clear: reduced labor costs, minimized material waste, and unprecedented architectural flexibility, yet their full potential hinges on mastering these foundational processes. As we move from theory to application in subsequent chapters, this knowledge becomes critical. By anchoring innovation in the principles of additive manufacturing, the construction industry can harness 3D printing not merely as a tool, but as a cornerstone of sustainable, rapid, and cost-effective building. The future of construction is being written layer by layer, and these fundamentals are its first blueprint. This introduction and conclusion for Chapter 2 establish the technical groundwork for 3D printing, linking its methodologies to practical construction benefits while setting the stage for deeper exploration of materials and applications in later chapters. Chapter 3: Global Trends in 3D Printed Construction. Introduction: the world is racing against time to address a dual crisis: exploding urbanization and a dire shortage of affordable housing. By 2030, over 1.6 billion people could lack adequate shelter, while aging infrastructure strains under climate change and population growth. Enter 3D printing, a technology reshaping the global construction landscape with solutions as bold as the challenges themselves. From the Netherlands' milestone of Europe's first 3D printed habitable home to Dubai's ambition to 3D print 25% of its buildings by 2030, this chapter explores how nations are leveraging additive manufacturing to build faster, cheaper, and smarter. We delve into three pivotal trends: the urgent demand for rapid and affordable housing, groundbreaking applications in infrastructure, think bridges in Madrid and flood-resistant schools in Malawi, and the evolving policy frameworks from California to Singapore that are turning experimental projects into mainstream practice. As 3D printing transitions from novelty to necessity, this chapter maps its global footprint, a story of innovation meeting desperation, and policy racing to keep pace. Conclusion: the global surge in 3D printed construction is more than a technological triumph, it's a blueprint for equitable, resilient urbanization. From slashing housing costs in India's slum upgrading projects to erecting disaster-resilient clinics in war-torn regions, additive manufacturing proves its power to democratize shelter and redefine infrastructure. Yet its potential remains tethered to policy ingenuity. Belgium's streamlined zoning codes for printed homes and Mexico's subsidies for sustainable materials exemplify how regulation can fuel adoption. Challenges persist: material standardization, skilled labor gaps, and public skepticism, but the trajectory is clear. As cities from Nairobi to New York embrace this paradigm, 3D printing emerges not just as a tool, but as a global movement. The question is no longer if it will reshape construction, but how swiftly policymakers, engineers, and communities can collaborate to scale its promise. The future of building is here, layer by layer, and it's leaving no continent behind. This chapter's introduction and conclusion emphasize 3D printing's role in addressing urgent global challenges, blending real-world examples with policy insights to illustrate its transformative potential and the collaborative efforts needed to unlock it. Chapter 4: Cement-based materials for 3D printing. Introduction: cement-based materials, the backbone of modern construction, are undergoing a radical transformation as they adapt to the demands of 3D printing. Traditional concrete, prized for its strength and durability, must now be re-engineered to meet the unique requirements of additive manufacturing: flowability for seamless extrusion, rapid setting to sustain layered structures, and cohesion to prevent collapse. This chapter explores the alchemy of printable concrete, where precise ratios of cement, aggregates, and water intersect with innovative additives like superplasticizers and viscosity modifiers to achieve the delicate balance between workability and structural integrity. From nanosilica enhancing early age strength to cellulose fibers mitigating cracking, we dissect the science behind optimizing cementitious mixes. Case studies, such as the 3D printed pedestrian bridge in Amsterdam and Habitat for Humanity's affordable housing projects, demonstrate how these tailored materials are turning digital blueprints into habitable realities, proving that the future of construction lies as much in chemistry as in code. Conclusion: the evolution of cement-based materials for 3D printing marks a paradigm shift in how we conceive and construct the built environment. By reimagining concrete's composition through advanced additives, precise rheological control, and sustainable alternatives like recycled aggregates, engineers are overcoming the limitations of traditional mixes. The success of projects like Italy's 3D printed eco-village and Icon's resilient homes in Texas underscores the viability of these innovations, blending speed with structural reliability. Yet challenges remain: scaling production, ensuring long-term durability, and reducing carbon footprints. As research pushes towards self-healing concretes and low-carbon binders, the lessons from this chapter lay a foundation for broader adoption. Cement, once a static commodity, is now a dynamic medium bridging ancient building traditions with a digital, sustainable future. The layers of progress, quite literally, are setting anew. This introduction and conclusion for Chapter 4 emphasize the transformative re-engineering of cement for 3D printing, balancing technical insights with real-world applications and future challenges, while aligning with the book's focus on innovation and sustainability. Chapter 5, Geopolymers and Alternative Binders. Introduction. As the construction industry grapples with the environmental toll of cement production responsible for 8% of global CO emissions, geopolymers and alternative binders emerge as revolutionary contenders in sustainable 3D printing. Unlike traditional Portland cement, geopolymers are synthesized from industrial byproducts like fly ash, slag, or metakaolin, activated by alkaline solutions to form durable, low-carbon matrices. These materials boast exceptional properties: high early strength, fire resistance, and resistance to chemical corrosion, making them ideal for additive manufacturing. This chapter explores the science behind geopolymers, their tailored rheology for seamless extrusion, and their role in reducing construction's ecological footprint. We also examine broader sustainable materials, such as clay-based mixes and bio-derived binders, that align with circular economy principles. Case studies, including the 3D-printed geopolymer pedestrian bridge in Beijing and the Vulcan project in Australia using mine waste, illustrate how these innovations are reshaping infrastructure, proving that green chemistry and cutting-edge technology can build a resilient future. Conclusion: geopolymers and alternative binders represent more than an eco-friendly substitute for cement. They signify a paradigm shift toward regenerative construction. By repurposing industrial waste into robust, 3D printable materials, these binders address both sustainability and performance demands. Projects like the Netherlands' 3D printed geopolymer facades and India's low-cost housing prototypes demonstrate their versatility, merging speed with environmental stewardship. Yet challenges persist: scaling production, standardizing alkaline activators, and navigating regulatory hurdles. Innovations in bio-based additives and carbon-negative formulations hint at a future where buildings sequester emissions rather than generate them. As the industry pivots from extraction to circularity, geopolymers and their kin stand at the vanguard, redefining resilience in the built environment. The path forward is clear: to build smarter, we must first build greener layer by sustainable layer. This introduction and conclusion frame geopolymers as both an environmental imperative and a technical breakthrough, aligning with the book's focus on innovation and sustainability while grounding abstract concepts in real-world applications and forward-looking solutions. Chapter 6, Composite Materials for 3D Printing. Introduction. In an era where construction demands both strength and sustainability, composite materials are redefining the possibilities of 3D printing. By synergizing polymers, fibers, and advanced additives, these materials transcend the limitations of traditional building components, offering unparalleled lightweight durability and design flexibility. This chapter delves into two groundbreaking categories: fiber-reinforced composites, where carbon, glass, or natural fibers embed within matrices to resist tension and fatigue, and polymer-based materials, which leverage thermoplastics and resins for rapid curing and intricate geometries. Together, they unlock applications ranging from aerospace-inspired, high-strength trusses to earthquake-resilient facades. Case studies like Germany's 3D printed fiber-reinforced pedestrian bridge and Singapore's polymer-based modular housing units illustrate how composites are not just materials, they are enablers of architectural ambition, merging efficiency with elegance in the race towards smarter, lighter, and greener construction. Conclusion: composite materials stand at the frontier of 3D printing's evolution, proving that strength need not come at the cost of sustainability or innovation. Fiber-reinforced composites, with their tailored resilience, and polymer-based systems, with their rapid adaptability, are dismantling old paradigms of weight and waste. Projects like Italy's 3D printed composite seawalls and NASA's Mars habitat prototypes underscore their transformative potential, even as challenges like recyclability, cost, and standardized testing persist. Yet the trajectory is undeniable. As bio-based fibers and self-healing polymers enter the fray, composites are poised to drive a new era of construction, one where structures are as lightweight as they are robust, as sustainable as they are striking. The lesson is clear: in the quest to build better, composites are not just an option, they are the blueprint for tomorrow's built environment. This chapter's introduction and conclusion emphasize the transformative role of composites in balancing performance and sustainability, anchoring technical insights in real-world applications while highlighting both achievements and future challenges in 3D printed construction. Chapter 7, Recycled and Sustainable Materials Introduction. The construction industry generates over 10 billion tons of waste annually, a staggering figure that underscores the urgency of rethinking material use in the age of climate crisis. Enter recycled and sustainable materials, the unsung heroes of 3D printing's green revolution. This chapter explores how industrial byproducts, demolition debris, and bio-based alternatives are being reborn as high-performance building materials. From pulverized concrete aggregate to upcycled plastic polymers, innovators are transforming waste streams into durable, printable composites that slash carbon footprints and costs. We delve into the science of processing construction waste into viable 3D printing feedstocks, the rise of eco-friendly binders like mycelium and rice husk ash, and pioneering projects such as the Netherlands' circular building made entirely of reusable biomaterials. These advancements are not just technical feats, they are blueprints for a circular economy, proving that sustainability and structural integrity can coexist. Conclusion: recycled and sustainable materials are rewriting the rules of construction, turning landfills into legacies. Case studies like Mexico's 3D printed homes using ocean plastics and India's Waste to Walls initiative repurposing industrial slag demonstrate that eco-conscious building is both viable and scalable. Challenges remain: standardizing heterogeneous materials, optimizing recycling logistics, and incentivizing green policies, but the momentum is undeniable. As startups and researchers pioneer closed-loop systems where buildings are deconstructed and reprinted like organic matter, the industry inches closer to a zero-waste future. The lesson is clear: sustainability is no longer a constraint but a catalyst for innovation. By embracing waste as a resource, 3D printing is not just constructing buildings, it's rebuilding the planet, one recycled layer at a time. This introduction and conclusion frame recycled materials as pivotal to sustainable construction, blending urgent environmental context with tangible innovations and real-world successes, while aligning with the book's focus on cost-effective, forward-thinking solutions. Chapter 8, Extrusion-Based 3D Printing Introduction. Extrusion-based 3D printing has emerged as a cornerstone of modern construction, offering a blend of precision, efficiency, and versatility unmatched by traditional methods. By depositing materials layer by layer through a controlled nozzle, this technology enables the creation of complex geometries with minimal waste, revolutionizing how we approach large-scale projects. This chapter delves into the principles of extrusion printing, the engineering nuances of equipment and nozzle design, and the transformative applications reshaping infrastructure globally. From rapid housing solutions to intricate architectural marvels, extrusion-based 3D printing stands at the forefront of a construction renaissance, marrying innovation with practicality. Principles of extrusion printing. Extrusion-based 3D printing operates on a foundational process, 1. Digital modeling. A 3D design is sliced into discrete layers using specialized software. 2. Material preparation. Construction-grade materials, e.g., cement-based mixes, geopolymers, are formulated for optimal viscosity and flow. 3. Layer deposition. A pump system forces material through a nozzle, depositing it along predefined paths. Each layer bonds to the previous one, relying on precise curing times and adhesion properties. 4. Structural integrity. Sequential layering ensures cohesion, with materials engineered to resist sagging or deformation during printing. Key considerations include material rheology, flow behavior, curing kinetics, and environmental factors, temperature, humidity, that influence print quality. Equipment and nozzle design. Equipment types. Gantry systems, ideal for large, static projects, e.g., houses, offering stability and scalability. Robotic arms, provide flexibility for complex geometries and on-site adaptability. Mobile printers, deployable for remote or disaster relief projects. Nozzle innovations, variable diameters, adjustable nozzles optimize material flow for structural versus decorative elements. Multi-material capability, dual nozzles enable hybrid structures, e.g., insulation cores with reinforced shells. Anti-clogging features, critical for continuous operation with particulate-rich materials like concrete. Applications in large-scale construction, affordable housing, projects like Icon's Vulcan printer in Texas and Apiscor's 24-hour home prints demonstrate rapid, cost-effective solutions for housing shortages. Infrastructure, Spain's 3D printed pedestrian bridge and Dubai's 3D printed office building showcase structural robustness and design innovation. Disaster relief, portable printers create emergency shelters in crisis zones, such as Unhabitat's initiatives in Kenya. Architectural artistry, free auto-inspired lightweight pavilions and organic geometries exemplify design freedom. Challenges and future directions, material consistency, ensuring uniform flow and curing across large prints. Regulatory frameworks, developing codes for 3D printed structural safety and durability. Sustainability, integrating recycled materials and reducing energy consumption in printing processes. Conclusion. Extrusion-based 3D printing is redefining construction, offering a scalable, sustainable, and creative alternative to conventional techniques. By mastering material science, refining equipment design, and embracing real-world applications, the industry is poised to overcome long-standing challenges of cost, speed, and environmental impact. As innovations like AI-driven automation and bio-based materials emerge, extrusion technology will continue to push boundaries, transforming blueprints into habitable realities and laying the foundation for a dynamic, resilient built environment. The future of construction is not just built, it is printed, layer by visionary layer. This chapter systematically explores extrusion-based 3D printing, linking technical principles to real-world impact, while addressing both current achievements and future challenges in the construction sector. Chapter 9, Powder-based 3D printing. Introduction. In the quest for precision and complexity, powder-based 3D printing has carved a niche in modern construction, offering unparalleled detail and material versatility. Unlike extrusion methods, which layer viscous materials, techniques like binder jetting and selective laser sintering, SLS, fuse fine powders ranging from silica sand to advanced ceramics into intricate, high-resolution structures. Binder jetting employs a liquid adhesive to bind particles layer by layer, while SLS uses lasers to sinter powders into solid forms, both enabling the creation of geometries once deemed unbuildable. This chapter explores the mechanics of these processes, the critical role of material properties and process parameters, and their groundbreaking applications in architectural ornamentation, lightweight components, and bespoke structural elements. As sustainability and customization drive demand, powder-based printing emerges as a key player in constructing tomorrow's detailed, resource-efficient built environment. Conclusion: powder-based 3D printing bridges the gap between industrial precision and architectural artistry, proving indispensable for projects demanding complexity and efficiency. From binder-jetted sandstone facades adorning Dubai's skyscrapers to SLS-fabricated titanium nodes in seismic-resistant frameworks, these methods unlock designs that defy traditional constraints. Challenges such as material costs, scalability, and post-processing remain, yet advancements in recyclable powders and hybrid systems hint at a future where waste-free, large-scale powder printing becomes mainstream. As industries embrace sustainability and digital customization, powder-based techniques stand poised to revolutionize not just how we build, but what we build, transforming granular potential into enduring, elegant structures. In the evolving narrative of construction, this chapter underscores a truth: sometimes, the finest details emerge from the smallest grains. This chapter's introduction and conclusion emphasize powder-based printing's unique strengths in precision and sustainability, aligning with the book's themes while balancing technical insights with real-world applications and forward-looking innovation. Chapter 10, Robotic and Automated Systems Introduction. The construction industry, long defined by manual labor and incremental innovation, is undergoing a seismic shift as robotic and automated systems redefine the art of building. Robotic arms, with their dexterity and precision, now sculpt intricate architectural forms once confined to digital renders, while gantry systems tower over construction sites, methodically layering materials into habitable structures at unprecedented speeds. These technologies are not standalone marvels, they are the backbone of a smarter ecosystem, integrated with IoT sensors and AI algorithms that optimize workflows, predict material needs, and ensure structural integrity in real time. From autonomous printers erecting disaster-resilient homes in 24 hours to AI-driven robots collaborating on skyscraper frameworks, this chapter explores how automation is transcending human limitations, delivering speed, safety, and sustainability. Through global case studies, we witness a future where construction sites buzz not with cacophonous chaos, but with the synchronized hum of machines building smarter. Conclusion: robotic and automated systems are more than technological feats, they are the architects of a new construction paradigm. Gantry systems and robotic arms, empowered by IoT and AI, have proven their mettle in projects like the DFAB house in Switzerland, where drones and robots collaborated to build a multi-story marvel, and Cobot's autonomous printers revolutionizing affordable housing in Africa. Yet challenges linger: high upfront costs, the need for cross-disciplinary expertise, and regulatory inertia. As AI evolves to predict structural stresses and IoT networks grow more resilient, the industry edges closer to fully autonomous construction sites. The promise is clear: a world where buildings rise faster, safer, and greener, with machines handling hazardous tasks and humans steering creativity. The blueprint for this future is already here, etched not in paper, but in code and steel. In the dance of robotics and algorithms, construction is no longer just an industry, it's a symphony of innovation. This chapter's introduction and conclusion frame robotic automation as a transformative force, blending technical innovation with real-world impact while addressing both achievements and challenges. The narrative emphasizes the synergy between hardware, robots, and intelligence, IoT/AI, illustrating a future where technology and humanity collaborate to build better. Chapter 11, Hybrid Construction Methods. Introduction. In the evolving landscape of construction, hybrid methods are emerging as a pragmatic fusion of innovation and tradition, blending the speed and design freedom of 3D printing with the reliability of conventional techniques. While 3D printing excels at creating complex geometries and reducing material waste, traditional methods remain indispensable for certain structural, mechanical, and regulatory requirements. This chapter explores how integrating these approaches unlocks new efficiencies, whether through 3D printed modular units assembled with steel frameworks or hybrid foundations combining printed concrete with traditional reinforcement. We delve into applications in modular and prefabricated construction, where hybrid workflows streamline off-site production and on-site assembly, and examine real-world projects that balance cutting-edge technology with time-tested practices. By marrying the old and the new, hybrid construction offers a versatile blueprint for sustainable, scalable, and cost-effective building in the 21st century. Conclusion: hybrid construction methods represent not just a technical evolution, but a strategic reimagining of how we build. Case studies like California's mighty buildings, where 3D printed modular walls integrate with traditional plumbing and electrical systems, demonstrate the synergy of speed and practicality. Similarly, projects in Germany and China highlight how printed concrete cores paired with steel frameworks achieve both aesthetic innovation and structural compliance. Challenges such as material compatibility, regulatory hurdles, and workflow integration persist, yet the benefits: reduced costs, accelerated timelines, and enhanced sustainability underscore the method's transformative potential. As industries embrace hybrid models, they pave the way for a future where 3D printing and tradition coexist, each amplifying the other's strengths. The lesson is clear: in the quest for progress, the most resilient solutions often lie at the intersection of old and new, where granular innovation meets enduring wisdom. This chapter frames hybrid construction as a balanced, adaptive approach, linking technical integration to real-world efficacy. The introduction sets the stage by contrasting innovation with tradition, while the conclusion emphasizes practical outcomes and future potential, aligning with the book's focus on scalable, cost-effective solutions. Chapter 12, Design Principles for 3D Printing in Construction 1. Introduction: 3D printing revolutionizes construction by introducing design paradigms that prioritize efficiency, customization, and innovation. This chapter explores key design principles: topology optimization, generative design, and customization, supported by real-world case studies. 2. Topology optimization and generative design definitions and concepts. Topology optimization, a computational method that removes material from non-critical areas, creating lightweight, efficient structures, e.g., lattice or organic shapes. Generative design, algorithms explore multiple design solutions based on constraints, loads, materials, and objectives, cost, sustainability, often inspired by biomimicry. Application in 3D printing enables complex geometries unachievable with traditional methods. Examples: optimized beams, foundations, or entire building layouts, e.g., MX3DS steel bridge in Amsterdam. Benefits and challenges. Benefits: material savings, up to 40%, reduced weight, enhanced structural performance. Challenges: computational demands, integration with existing workflows, printer limitations. Tools and software: ANSI, Autodesk Fusion 360, generative design, Rhino/Grasshopper for parametric modeling. 3. Customization and personalization in building design. Role of 3D printing shifts from mass production to mass customization, enabling bespoke designs without cost penalties, e.g., unique facades, adaptive housing. Architectural implications: freedom in aesthetics, curved walls, intricate patterns, and functionality, client-specific layouts. Sustainability: reduced waste through precise material deposition. Challenges: scalability, regulatory compliance, and ensuring structural integrity in non-standard designs. Examples: Icon's Vulcan-printed homes in Texas with client-tailored features. Tekla, Italy, eco-habitat using local clay, customized for environmental harmony. 4. Case studies of innovative 3D printed structures. Case study 1, Dubai's Office of the Future, Design Principle, Generative Design for Modular Components. Innovation: world's first 3D printed office, reducing labor by 50% and waste by 30%. Material: cement mixture with reinforced layers. Case Study 2, Gaia House, Italy, Design Principle, Customization using natural materials, rice husk, clay. Outcome, sustainable, climate-responsive structure with near-zero waste. Case Study 3, Perry Group's DFAB House, Germany, integration, combines topology optimization, lightweight slabs, and generative design, spatial layout. Result, energy-efficient, multi-story residential unit validated by ETH Zurich. 5. Conclusion: 3D printing transforms construction through efficiency, topology optimization minimizes material use. Creativity, generative design unlocks novel solutions. Personalization, customized housing becomes scalable and sustainable. Future directions, advancements in AI-driven design, hybrid materials, and regulatory frameworks will further solidify 3D printing's role in architecture. Key takeaways: software interoperability and post-processing remain critical challenges. Case studies demonstrate the synergy of design principles and practical feasibility. Ethical considerations, equity in housing, warrant further exploration as the technology matures. This chapter underscores how 3D printing is not merely a construction tool but a catalyst for reimagining design possibilities in the built environment. Chapter 13, Structural Integrity and Performance in 3D Printed Buildings 1. Introduction: 3D printed construction challenges traditional paradigms by introducing novel materials and fabrication techniques. This chapter addresses the structural integrity of 3D printed buildings through three pillars: mechanical properties of printed materials, testing and quality control protocols, long-term durability and maintenance strategies. 2. Mechanical properties of 3D printed materials. Common materials, concrete, dominates construction due to adaptability, exhibits anisotropic behavior due to layer deposition. Polymers, used for lightweight components but vulnerable to UV degradation. Metals/composites, emerging for specialized applications, e.g., steel reinforcements. Key properties: compressive strength, comparable to traditional concrete but varies with layer bonding. Tensile strength, often lower, necessitating reinforcement, e.g., steel fibers, rebar. Elasticity/stiffness, layer orientation impacts flexibility. Influencing factors: print parameters, speed, nozzle size, and layer height affect porosity and adhesion. Curing, hydration in concrete or cooling rates in metals alter microstructure. Case example: Wasp's Tekla House, clay-based material optimized for compressive strength and thermal stability. 3. Testing and quality control. Testing methods: non-destructive evaluation, NDE, ultrasound, X-ray tomography, and infrared thermography to detect voids or delamination. Destructive testing, ASTM/ISO standards for compressive/tensile strength, e.g., ASTM C39 for concrete. In situ monitoring, sensors embedded during printing to track layer adhesion, temperature, and humidity. Challenges: lack of standards, existing protocols lag behind technological advancements. Material variability, inhomogeneity in recycled or novel materials. Case example: MX3DS steel bridge, real-time stress testing validated load-bearing capacity. 4. Long-term durability and maintenance. Environmental impacts, weathering, freeze-thaw cycles in concrete, UV degradation in polymers. Moisture ingress, layer interfaces as potential weak points for corrosion. Maintenance strategies, repair techniques, grouting for cracks, polymer coatings for UV protection. Monitoring systems, IoT sensors for early detection of structural degradation. Sustainability considerations, life cycle analysis, reduced waste versus potential for shorter material lifespans. Case example: Dubai's 3D printed office, accelerated aging tests simulated 20-year durability. 5. Regulatory and future directions. Building codes, gaps, few codes address anisotropic materials or layer-dependent design. Certification, collaboration needed between regulators and industry, e.g., ICC evaluation reports. Research frontiers, AI-driven predictive models, for fatigue and creep behavior. Hybrid materials, combining polymers, metals, and bio-based composites. 6. Conclusion: structural integrity in 3D printed construction hinges on material innovation, tailoring properties for printability and performance. Rigorous testing, bridging the gap between novel methods and standardized protocols. Proactive maintenance, ensuring longevity in diverse environments. Key takeaways: anisotropy and layer adhesion are critical design constraints. Interdisciplinary collaboration is vital to advance testing standards. Long-term data collection is essential to validate durability claims. This chapter underscores that 3D printing's success in construction relies not only on design creativity but also on engineering rigor to meet structural demands. Figures/table suggestions: 1. Comparison of compressive strength, 3D printed versus cast-in-place concrete. 2. Diagram of NDE techniques for layer integrity. 3. Life cycle analysis flowchart for 3D printed versus traditional buildings. References: ASTM International, ISO, and ETH Zurich studies on material testing. Case studies from WASP, MX3D, and Dubai Municipality. This framework balances technical depth with accessibility, ensuring relevance for engineers, architects, and policymakers alike. Chapter 14, Thermal and Acoustic Properties of 3D Printed Buildings. 1. Introduction: 3D printing introduces innovative solutions to optimize thermal and acoustic performance in buildings, critical for energy efficiency and occupant comfort. This chapter explores how material choices, design strategies, and fabrication techniques address insulation, soundproofing, and their applications in residential and commercial contexts. 2. Insulation and energy efficiency material innovations, concrete composites, enhanced with aerogels, foams, or recycled aggregates to improve thermal resistance, revalue. Bio-based materials, hempcrete or mycelium-infused mixes for sustainable insulation. Multi-material printing, layered structures with alternating insulating and structural materials, e.g., polymer foam sandwiched between concrete. Design strategies, geometric optimization, hollow walls, lattice infills, or air gaps to reduce thermal bridging. Passive design integration, curved surfaces for solar gain management or shaded overhangs printed in situ. Case studies: Tekla House, Italy. Clay walls with organic geometries that balance thermal mass and insulation for Mediterranean climates. Icon's Vulcan system, printed homes in Texas using insulated concrete to minimize HVAC loads. Challenges: material consistency, ensuring uniform insulation properties across layers. Code compliance, meeting energy standards, e.g., OSHRI, passive AOS, with novel materials. 3. Soundproofing and acoustic performance material and structural solutions, porous materials, lightweight concrete with air voids or polymer composites for sound absorption. Resonant structures, printed wave-like geometries or internal baffles to disrupt sound transmission. Hybrid systems, integrating acoustic panels or mineral wool during printing. Testing and metrics, sound transmission class, STC measures airborne noise reduction, e.g., walls achieving STC 50+, impact insulation class, IIC critical for floor/ceiling assemblies in multi-story buildings. Case studies: Dubai's 3D printed office, custom wall textures reduce echo in open-plan spaces. Waspskaya module, rice husk-infused walls provide natural sound dampening. Challenges: layer adhesion, weak interfaces may compromise acoustic seals. Frequency variability, balancing low frequency, e.g., traffic, versus high frequency noise control. 4. Applications in residential and commercial buildings. Residential use, energy efficient homes, printed walls with integrated insulation for net zero designs. Noise-reduced housing, urban dwellings near highways using acoustic-optimized materials. Commercial use, office space, sound-absorbing partitions and thermal mass for climate control. Hospitality, customized acoustic environments, e.g., hotels near airports. Sustainability synergy, reduced waste, precise material deposition lowers excess insulation/paneling. Life cycle benefits, durable thermal/acoustic solutions minimizing retrofits. 5. Challenges and future directions. Technical hurdles, hybrid systems, combining 3D printing with traditional insulation/acoustic methods. Long-term performance, monitoring degradation of insulating materials under UV/moisture. Innovation frontiers, smart materials, phase change materials, PCMs, for adaptive thermal regulation. AI-driven design, algorithms optimizing geometry for site-specific thermal/acoustic needs. Regulatory gaps, standardization, developing codes for 3D printed assemblies, e.g., ASTM/ISO. Global adaptation, tailoring solutions to tropical, arid, or cold climates. 6. Conclusion. 3D printing redefines building performance by merging thermal efficiency and acoustic comfort with design freedom. Key advancements include, material hybridization, balancing structural and functional properties. Passive design integration, reducing reliance on mechanical systems. Scalability, from single-family homes to large commercial complexes. Key takeaways, thermal bridges and layer adhesion remain critical challenges. Interdisciplinary collaboration is vital for holistic solutions. Case studies demonstrate feasibility but underscore the need for long-term data. Figures/table suggestions, 1 thermal imaging comparison, 3D printed versus conventional walls. 2 STC/IIC ratings of common 3D printed materials. 3 cross-section of a 3D printed wall with integrated insulation and acoustic layers. References, OSHRI standards, Passive AOS Institute criteria. Case studies from ICON, WASP, and Dubai Municipality. Research from ETH Zurich on multi-material printing. This chapter positions 3D printing as a transformative tool for creating energy-efficient, quiet, and adaptable built environments, urging further innovation and standardization. Chapter 15, Integration with Smart Building Systems in 3D Printed Construction. 1. Introduction. 3D printing and smart technologies are converging to redefine modern construction, enabling buildings that are not only structurally innovative but also adaptive, energy efficient, and interconnected. This chapter explores how IoT-enabled systems, smart city frameworks, and sustainable development goals synergize with 3D printed structures, supported by real-world case studies. 2. IoT-enabled 3D printed buildings. Core concepts, embedded sensors, printed directly into walls or structural components to monitor temperature, humidity, stress, and occupancy. Automation, integration of smart HVAC, lighting, and security systems controlled via IoT platforms, e.g., BACnet, KNX. Applications, structural health monitoring, SHM real-time detection of cracks, vibrations, or material fatigue, e.g., MX3DS sensor laden steel bridge, energy management, AI-driven systems optimizing HVAC based on occupancy and weather data. Adaptive spaces, walls with shape memory alloys or actuators for reconfigurable layouts. Technologies and tools, edge computing, local data processing to reduce latency, e.g., NVIDIA Jetson. Wireless protocols, LoRaWAN, Zigbee, or 5G for seamless connectivity. Challenges, power supply, energy harvesting, solar, piezoelectric, for embedded sensors. Interoperability, standardizing communication between diverse IoT devices. Cybersecurity, protecting data integrity in connected systems. 3. Applications in smart cities and sustainable development. Urban scalability, Rapid housing, deploying 3D printed, IoT integrated homes for growing populations, e.g., India's Housing for All initiative. Modular infrastructure, printed bus stops, pedestrian bridges, or utility hubs with embedded environmental sensors. Sustainability synergies, energy-neutral buildings, solar panels printed onto facades and IoT-driven demand response systems. Circular economy, smart material tracking for recycling printed components. Smart city integration, grid interaction, buildings as prosumer storing/releasing energy to smart grids. Mobility links, proximity to 3D printed EV charging stations or micro-mobility hubs. Policy and governance, data-driven urban planning, IoT data from printed buildings informing citywide resource allocation. Regulatory frameworks, updating codes to address IoT infrastructure in 3D printed projects. 4. Case studies of smart 3D printed structures. Case study 1, Dubai's 3D printed smart office, IoT features, occupancy sensors, automated shading, and energy use dashboards. Impact, 30% reduction in energy consumption compared to conventional offices. Case study 2, Tecla Eco Habitat, Italy, smart systems, humidity and temperature sensors in clay walls for passive climate control. Sustainability, near zero waste and integration with local renewable energy grids. Case study 3, Icon's Resilient Home, USA, IoT integration, flood sensors and emergency communication systems for disaster-prone areas. Scalability, replicable design for community-wide climate resilience. 5. Challenges and future directions. Technical barriers, material limitations, conductive inks or printable electronics for seamless IoT integration. Scalability, balancing customization with mass production in smart city projects. Innovation frontiers, AI and digital twins, predictive maintenance using real-time IoT data. Blockchain, securing IoT data exchanges in smart buildings. 4D printing, structures that self-adapt to environmental stimuli, e.g., temperature, light. Ethical considerations, data privacy, managing occupant data collected by IoT systems. Equity, ensuring smart 3D printed housing is accessible to low-income communities. 6. Conclusion. The fusion of 3D printing and smart systems unlocks transformative potential, resilience, buildings that self-monitor and adapt to environmental stresses. Efficiency, IoT-driven resource optimization reducing operational costs. Inclusivity, scalable solutions addressing urbanization and climate challenges. Key takeaways, interdisciplinary collaboration, engineers, data scientists, policymakers, is critical. Pilot projects must prioritize long-term performance data and user feedback. Ethical frameworks are needed to govern IoT data and equitable access. Figures/table suggestions, 1 diagram of IoT sensor networks in a 3D printed building. 2 comparison of energy savings, smart 3D printed versus traditional buildings. 3 map of a smart city ecosystem integrating 3D printed infrastructure. References, IoT standards, ISO/IEC 30141, IEEE, case studies from ICON, WASP, and Dubai. Research on 4D printing from MIT and Singapore University of Technology and Design. This chapter positions 3D printing as a cornerstone of next-generation smart cities, where buildings are dynamic, responsive, and integral to sustainable urban ecosystems. Chapter 16, Affordable Housing and Rapid Construction with 3D Printing. 1. Introduction. The global housing crisis, exacerbated by population growth, urbanization, and climate disasters, demands innovative solutions. 3D printing emerges as a transformative tool for affordable housing and rapid construction, offering cost-effective, scalable, and sustainable alternatives. This chapter explores its applications in disaster relief, case studies of low-cost homes, and benefits for underserved communities. 2. Applications in disaster relief and emergency housing. Key advantages: speed, print a basic shelter in 24 hours, versus weeks for traditional methods. Cost, up to 50% savings on labor and materials. Adaptability, use of local materials, clay, recycled concrete, in resource-scarce regions. Case examples: Icons Operation Phoenix, USA deployed 3D printed homes for wildfire survivors in California, integrating fire-resistant materials. 14TREES, Africa/Malawi printed emergency shelters post-cyclones using low-carbon cement. WASP's Crane 3D printer, deployed in earthquake-stricken regions, e.g., Turkey, for rapid housing. Challenges: logistics, transporting printers to remote/disaster zones. Durability, ensuring temporary shelters meet safety standards for extreme weather. Community engagement, aligning designs with cultural preferences. 3. Case studies of affordable 3D printed homes. Case study 1, Tecla, Italy. Material, locally sourced clay and rice husk. Cost, $6,000 per unit. Impact, zero waste circular design for sustainable communities. Case study 2, Icons Community First. Village, USA, mission, housing for chronically homeless in Austin, Texas. Features, 400 square foot homes printed in 24 hours at $10,000 each. Scalability, replicated in Mexico for low-income families. Case study 3, T-Vasta, India. Design, affordable single-story homes using recycled concrete. Cost, 30% cheaper than conventional builds. Goal, support India's Housing for All initiative by 2024. Comparison to traditional methods. Metric 3D printed home. Traditional home construction time 17 days 3-6 months. Labor costs 70% reduction. High material waste 10% 30% 4. Benefits for low-income and underserved communities. Economic empowerment, job creation, training locals in 3D printing operations and maintenance. Reduced debt, affordable mortgages for sub $20,000 homes, e.g., mighty buildings in California. Sustainability and health, energy efficiency, insulated designs lower utility bills. Non-toxic materials, minimize respiratory issues from traditional construction dust. Social equity, cultural customization, designs reflecting local aesthetics, e.g., curved walls in Middle Eastern projects. Land rights, partnerships with governments to secure tenure for informal settlements. Challenges, technology access, high printer costs in developing regions. Maintenance literacy, training residents to repair printed structures. Policy barriers, zoning laws favoring conventional builds. 5. Future directions and scalability innovations, mobile printers, truck-mounted systems for on-site printing in remote areas. AI-driven design, optimizing layouts for density and community needs, e.g., shared spaces. Policy recommendations, subsidies, government grants for 3D printed social housing. Standards, developing codes for printed homes in collaboration with NGOs, e.g., Unhabitat. Ethical consideration, equity, preventing tech-driven gentrification in low-income areas. Cultural sensitivity, avoiding one-size-fits-all designs in diverse regions. 6. Conclusion: 3D printing redefines affordable housing by democratizing access, bridging the gap between housing demand and supply. Accelerating recovery, providing dignified shelter in crises. Promoting sustainability, reducing carbon footprints and waste. Key takeaways: success hinges on community involvement and adaptive designs. Partnerships between governments, NGOs, and tech firms are critical. Long-term studies are needed to validate durability and social impact. Figures/table suggestions, 1 timeline comparison, 3D printed versus traditional disaster housing. 2 Map of global 3D printed affordable housing projects. 3 Cost breakdown of a 3D printed home, materials, labor, overhead. References, Unhabitat reports on global housing shortages. Case studies from ICON, 14TREES, and T-Vasta. Research on social impact by MIT D-Lab and ETH Zurich. This chapter positions 3D printing as a catalyst for equitable, resilient communities, urging stakeholders to prioritize inclusivity and sustainability in scaling solutions. Chapter 17, Infrastructure and Large-Scale Projects in 3D Printed Construction 1. Introduction. 3D printing is revolutionizing infrastructure development by enabling rapid, cost-effective, and sustainable solutions for bridges, tunnels, and roads. This chapter explores current applications, case studies, and future innovations in large-scale 3D printed infrastructure, emphasizing design freedom, material efficiency, and resilience. 2. Bridges design and construction. Steel bridges. MX3DS robotic welding in Amsterdam produced a 12-meter steel bridge, optimized via generative design for weight reduction and structural efficiency. Concrete bridges. China's 3D printed pedestrian bridge in Shanghai, 2019, used ABS plastic molds and fiber-reinforced concrete, completed in 450 hours. Benefits: complex geometries, curved or lattice structures unachievable with traditional methods. Speed: MX3DS bridge reduced construction time by 50% compared to conventional steel fabrication. Challenges: material certification, ensuring long-term durability under dynamic loads. Cost: high initial investment for specialized printers. 3. Tunnels innovative applications. Segment printing. BOD2 printer, COBOD, creates tunnel lining segments using reinforced concrete, tested in European pilot projects. In situ reinforcement, embedding steel meshes during printing for enhanced stability. Case study: Dubai's 3D printed tunnel, modular segments printed off-site and assembled, reducing on-site labor by 30%. Challenges: underground complexity, managing water ingress and soil pressure. Scalability, printer size limitations for large diameter tunnels. 4. Roads material and methods. Concrete roads, Netherlands Cycle Path, 2017, used 3D printed concrete slabs with integrated sensors for traffic monitoring. Asphalt alternatives, research into polymer modified asphalt for extrusion-based printing. Benefits: rapid repair, localized printing minimizes traffic disruption. Sustainability: 30% less material waste compared to traditional paving. Challenges: durability, wear resistance under heavy traffic and freeze-thaw cycles. Regulatory gaps, lack of standards for 3D printed road surfaces. 5. Case studies of 3D printed infrastructure. Case study 1, MX3D steel bridge, Netherlands, innovation, sensor embedded for real-time stress monitoring. Impact: reduced labor costs and CO2 emissions by 40%. Case study 2, Eindhoven cycle path, Netherlands, design, hexagonal concrete tiles for easy replacement and water drainage. Outcome: 70% faster installation than traditional methods. Case study 3, U.S. Army's 3D printed barracks bridge, mission, rapid deployment in remote areas using on-site concrete printing. Result: 50% cost reduction and 3-day construction timeline. 6. Future directions for large-scale applications. Technological advancements, AI-driven design, generative algorithms for topology-optimized, lightweight structures. Autonomous printers, solar-powered systems for off-grid infrastructure in disaster zones. Hybrid construction, combining 3D printing with prefab modules for skyscraper foundations. Material innovations, recycled composites, integrating plastic waste into road and bridge materials. Self-healing concrete, microcapsules releasing repair agents upon crack detection. Policy and sustainability, Standardization, ASTM/ISO codes for 3D printed infrastructure certification. Circular economy, closed-loop systems for reusing printed components. 7. Challenges and ethical considerations, public acceptance, overcoming skepticism about structural reliability. Equity, ensuring access to 3D printing tech in developing regions. Carbon footprint, balancing energy use with life cycle sustainability gains. 8. Conclusion: 3D printing is poised to transform global infrastructure through speed and cost efficiency, accelerating project timelines by up to 60%. Resilience, adaptive designs for climate-resilient bridges and roads. Sustainability, reducing material waste and embodied carbon. Key takeaways: collaboration between governments, engineers, and tech firms is critical. Pilot projects must prioritize long-term performance data and scalability. Ethical frameworks should guide equitable technology deployment. Figures/table suggestions: 1. Cross-section of 3D printed tunnel segments with embedded sensors. 2. Cost/time comparison, 3D printed versus traditional infrastructure projects. 3. World map highlighting major 3D printed infrastructure initiatives. References: MX3DS Bridge White Papers, COVID case studies, and Dutch road projects. Research from TU Eindhoven and MIT on self-healing materials. This chapter underscores 3D printing's potential to address 21st century infrastructure challenges, urging stakeholders to embrace innovation while addressing technical and societal barriers. Chapter 18, Artistic and Architectural Applications of 3D Printing. 1. Introduction: 3D printing has revolutionized the realms of art and architecture by transcending traditional manufacturing constraints. This chapter explores how the technology enables custom geometries, fosters architectural innovation, and redefines aesthetic and functional paradigms through case studies and forward-looking insights. 2. Custom and complex geometries: design freedom, intricate forms, facilitates organic, lattice, and parametric designs, e.g., branching structures inspired by nature. Generative algorithms, tools like Grasshopper and Autodesk Fusion 360 automate complex geometry generation. Material efficiency, lightweight, topology-optimized structures minimize waste, e.g., Zaha Hadid architects sinuous forms. Tools and techniques: parametric modeling, Rhino and Grasshopper for iterative, algorithm-driven designs. Multi-material printing, layering concrete, polymers, or metals for hybrid textures. Examples: the Bloom Pavilion, USA 3D printed sandstone panels forming a porous, flower-like structure. Coral reef installations, mimicking marine ecosystems with intricate, layered designs. 3. Case studies of artistic 3D printed structures. Case study 1, Eladio Diest's Digital Revival, Uruguay, Innovation, 3D printed reinterpretations of Diest's brick vaults using PLA. Impact, merges historical craftsmanship with modern additive manufacturing. Case study 2, The Twisting Towers, Dubai, Design, fluid, helical facades printed with carbon fiber reinforced polymer. Sustainability, reduced material use by 35% compared to steel frameworks. Case study 3, Waspskaya House, Italy, material, clay and rice husk composite. Aesthetic, curvilinear walls blending vernacular architecture with futuristic form. 4. Role of 3D printing in architectural innovation. Workflow transformation, rapid prototyping, architects iterate designs digitally before full-scale printing. On-site customization, printers adjust designs in real time for adaptive urban spaces. Sustainability, local materials, earth-based mixes, clay, hempcrete, reduce transport emissions. Circular design, recyclable structures, e.g., 3D printed mycelium modules. Aesthetic evolution, bio-inspired design, biomimicry in facades, e.g., honeycomb patterns for strength and ventilation. Interactive art, kinetic sculptures with embedded sensors responding to environmental stimuli. 5. Challenges, material limitations, durability of printable artistic materials under UV/weather exposure. Scale constraints, printer size restricts monumentality, solved via modular assembly. Cost, high-end printers and materials remain prohibitive for small studios. 6. Future directions, technological advances, hybrid construction, combining 3D printing with robotic assembly for large installations. AI-driven art, machine learning algorithms generating culturally resonant designs. Sustainability focus, recycled materials, ocean plastics or construction waste repurposed for artistic prints. 4D printing, time-responsive structures adapting to environmental changes. Interdisciplinary collaboration, artist-engineer partnerships, bridging aesthetics with structural integrity. Educational shifts, universities integrating 3D printing into architecture and fine arts curricula. 7. Conclusion: 3D printing is a catalyst for artistic and architectural evolution, offering unprecedented creativity, from fractal sculptures to adaptive buildings. Sustainable practices, localized production and waste reduction. Democratization, affordable tools empowering emerging artists and architects. Key takeaways: balancing innovation with structural feasibility remains critical. Ethical considerations around cultural appropriation and environmental impact must guide progress. The fusion of art, technology, and ecology will define future urban landscapes. Figures/tables suggestions, 1 visual timeline of 3D printed architectural milestones. 2 comparison table, traditional versus 3D printed architectural elements, cost, time, waste. 3 cross-section of a 3D printed bio-inspired facade. References: Zaha Hadid Architects Parametric Design Research. Case studies from WASP, Emerging Objects, and COBID. Journals: 3D Printing and Additive Manufacturing, Architectural Design. This chapter underscores 3D printing as a transformative medium, bridging artistry and engineering to shape resilient, imaginative built environments. Chapter 19, Technical and Engineering Challenges in 3D Printed Construction. 1. Introduction: 3D printing in construction holds transformative potential, promising speed, cost efficiency, and design innovation. However, its widespread adoption faces significant technical and engineering challenges. This chapter examines 3 critical hurdles: material limitations, scalability and speed, and integration with building codes, while outlining pathways to overcome them. 2. Material limitations and process optimization. Key challenges: material suitability, concrete, requires precise viscosity and setting time for extrusion, improper mixes risk clogging nozzles or poor layer adhesion. Durability, weather resistance, long-term strength, and fire performance of novel materials, e.g., polymers, composites, remain unproven. Material diversity, limited options compared to traditional construction, e.g., steel, wood. Process optimization, layer bonding, weak interlayer cohesion can compromise structural integrity. Environmental factors, temperature and humidity affect curing and material behavior. Software algorithms, need for path planning tools to balance speed, material use, and strength. Solutions and innovations, advanced materials, fiber-reinforced concrete, geopolymers, and bio-based composites. Self-healing concrete with embedded microcapsules. Process enhancements, real-time monitoring systems to adjust printing parameters, e.g., nozzle speed, material flow. Post-processing techniques like robotic grinding or UV curing. Case study: Icon's Vulcan system, uses proprietary concrete mix optimized for layer adhesion and rapid curing in diverse climates. 3. Scalability and speed of construction. Key challenges: printer size limitations, large-scale projects require massive gantry systems or mobile printers, complicating logistics. Speed-quality trade-offs, faster printing may reduce resolution or structural performance. Multi-story complexity, printing upper floors demands precise alignment and support structures. Solutions and innovations, modular printing, off-site fabrication of components, e.g., walls, floors, for on-site assembly. Swarm robotics, multiple printers collaborating on a single structure to accelerate timelines. Hybrid techniques, combining 3D printing with traditional methods, e.g., steel frameworks for high-rises. Case study, Kobod's BOD2 printer, used in Germany to print a 3-story building, demonstrating scalability through modular design. 4. Integration with existing building codes and standards. Key challenges, regulatory gaps, most codes, e.g., IBC, Eurocodes, lack provisions for 3D printed structures. Certification, no standardized tests for material performance or structural safety. Liability, ambiguity in responsibility for failures, designer, printer manufacturer, or material supplier. Solutions and innovations, pioneering regulations. Dubai mandates 25% of new buildings to be 3D printed by 2030, with tailored safety guidelines. USA, ICCES evaluation reports for 3D printed walls. Collaborative frameworks, partnerships between governments, academia, and industry to draft codes, e.g., ASTM International's Additive Manufacturing Committee. Case study, Habitat for Humanity's 3D printed home, collaborated with local authorities in Virginia to align with IRC codes, setting a precedent for U.S. approvals. 5. Future directions, material science, development of smart materials, e.g., carbon capturing concrete, phase change composites. AI integration, machine learning for real-time defect detection and adaptive printing. Global standards, harmonized international codes to facilitate cross-border projects. Education, training programs for architects, engineers, and inspectors on 3D printing technologies. 6. Conclusion. While 3D printing in construction faces formidable challenges, interdisciplinary collaboration and technological innovation are paving the way for solutions. Addressing material limitations, scaling production, and aligning with regulatory frameworks will be critical to realizing its full potential. The industry must prioritize research, standardization, and education to transform these challenges into opportunities for sustainable, resilient built environments. Key takeaways: material innovation and process optimization are foundational to overcoming technical barriers. Scalability requires rethinking both printer technology and construction methodologies. Regulatory evolution must keep pace with technological advancements to ensure safety and public trust. Figures/tables suggestions, 1. Comparison of traditional versus 3D printed material properties. 2. Infographic on modular versus monolithic 3D printing workflows. 3. Global map of regions with 3D printing construction codes. References: Dubai Municipality's 3D printing strategy. ASTM International Standards, e.g., F42 Committee. Case studies from ICON, Kobod, and Habitat for Humanity. This chapter underscores that overcoming technical and engineering challenges is not merely a matter of innovation but of systemic collaboration across disciplines and industries. Chapter 20, Economic and Social Considerations in 3D Printed Construction. 1. Cost-effectiveness and market adoption. Economic analysis, initial costs, high capital investment in printers, e.g., ICON's Vulcan system costs $1M, and proprietary materials, e.g., Lafarge Holcim's Tector print. Operational savings, labor, 50–80% reduction in manual labor, e.g., 14 Trees Malawi project cut labor costs by 70%, material waste, 10% versus 30% in traditional construction. Speed, 3D printing a 600 square foot home in 24 hours, ICON, versus weeks conventionally metric 3D printing traditional cost per square foot $4 $12, varies by region, $10 $20 construction time days weeks months labor intensity. Low-high market adoption drivers, regulatory push, Dubai's 2030 mandate for 25% 3D printed buildings. Affordable housing, projects like T-Vasta's $10,000 homes in India align with UN Sustainable Development Goals. Startups versus incumbents, startups, Icon, Cobot, Lead Innovation, traditional firms, Skanska, Vinci, pilot hybrid approaches. Barriers, material costs, limited suppliers inflate prices, e.g., specialized concrete mixes. Scalability, large-scale projects require printer mobility/modularity, e.g., WASP's crane. 2. Workforce training and skill development. Emerging skill gaps, technical skills, CAD modeling, Rhino/Grasshopper, printer operation and robotics maintenance. New roles, additive manufacturing engineers, material scientists. Training initiatives, corporate programs, Icon's partnerships with vocational schools to train operators. Academic integration, Zurich's MOS in digital fabrication, MIT's additive construction courses. Global disparities, developing nations face challenges accessing training infrastructure. Labor market impact, job displacement, reduced demand for traditional masons and carpenters. Job creation, 3D printing roles could grow by 15% annually, McKinsey, 2023. 3. Public perception and acceptance. Key factors, safety concerns, 58% of respondents in a 2023 Ecom survey doubted fire/earthquake resistance. Aesthetics, layered concrete textures versus traditional finishes, solutions include cladding, e.g., mighty buildings composite panels. Cultural fit, projects like WASP's Tekla, Italy, blend vernacular design with 3D printing. Case studies in trust building. Disaster relief, Icon's wildfire-resistant homes in California improved local acceptance. Community CO design, fostering ownership through participatory design, e.g., 14 Trees Malawi shelters. Media influence, positive, Netflix is the future of us showcasing 3D printed homes. Negative, viral videos of early print failures fueling skepticism. 4. Social equity considerations, accessibility, 3D printing can lower housing costs but risks tech concentration in urban areas. Policy solutions, subsidies for rural printer deployment, e.g., India's Housing for All. Ethical risks, gentrification if tech-driven projects displace informal settlements. 5. Conclusion and future directions, economic synergy, pair cost savings with policy incentives, tax breaks, grants, to accelerate adoption. Workforce evolution, global upskilling partnerships, UNESCO, World Bank, to bridge skill gaps. Public engagement, transparent marketing and demo homes to demystify technology. Key takeaways, 3D printing's ROI hinges on scaling production and regulatory alignment. Social acceptance requires addressing aesthetic, safety, and cultural concerns. Equity must be central to deployment strategies to avoid exacerbating inequalities. Figures/table suggestions, 1 infographic, cost breakdown of a 3D printed versus traditional home. 2 map, global hotspots for 3D printed construction, Dubai, USA, India. 3 survey data, public perception trends, safety, aesthetics, across regions. References, Dubai 3D Printing Strategy, 2023. McKinsey & Company, The Future of Construction, 2023. Case studies from Icon, 14TREES, and WASP. This chapter underscores that 3D printing's success depends not only on technical prowess but on harmonizing economic viability, workforce readiness, and societal trust. Chapter 22, Commercial projects using 3D printing. 1. Examples of 3D printed buildings and infrastructure. 1.1 Dubai's Office of the Future, UAE, 2016, Project Overview, the world's first fully functional 3D printed office, commissioned by the Dubai government. Technology/materials, cement mixture reinforced with fiber reinforced plastic, printed using a 20-foot 3D printer. Outcomes, completed in 17 days, reduced labor costs by 50%, and achieved LEED Platinum sustainability certification. 1.2 Icons Community First Village, USA, 2020 Present, Project Overview, Affordable Housing Community in Austin, Texas, for the chronically homeless. Technology/materials, Vulcan 2 printer using proprietary lavacrete, cement-based material. Outcomes, 400 square foot homes printed in 24 hours, scalable model for low-income housing. 1.3 MX3DS Steel Bridge, Netherlands, 2021, Project Overview, 12-meter stainless steel pedestrian bridge in Amsterdam, designed with generative algorithms. Technology/materials, robotic welding arms for metal additive manufacturing, embedded sensors for real-time monitoring. Outcomes, reduced material waste by 40%, showcase structural viability of 3D printed metal. 1.4 Wasps Tekla House, Italy, 2021, Project Overview, Eco-habitat using locally sourced clay and rice husk. Technology/materials, crane wasp printer with dual extruders, zero-waste circular design. Outcomes, 60 square m structure completed in 200 hours, demonstrated sustainable rural housing solutions. 1.5 Perry Group's DFAB House, Germany, 2021, Project Overview, multi-story residential unit combining 3D printing with robotic prefab. Technology/materials, Cobalt BOD2 printer, lightweight concrete slabs. Outcomes, 60% faster construction, validated hybrid construction methods. 2. Lessons learned and best practices. Key lessons, material innovation, projects like Tekla highlight the need for locally sourced, sustainable materials. Regulatory navigation, Dubai's office set a precedent for municipal approvals, emphasizing early engagement with regulators. Cost efficiency, Icons projects show labor savings but underscore high initial printer investments. Best practices. 1. Design for additive manufacturing, use topology optimization, e.g., MX3DS bridge, to minimize material use. 2. Collaborative stakeholder engagement, involve architects, engineers, and policymakers early, e.g., Perry Group's DFAB House. 3. Iterative prototyping, test small-scale prototypes to refine print parameters, e.g., WASP's iterative clay trials. 4. Public-private partnerships, leverage partnerships for funding and scaling, e.g., Icons collaboration with nonprofits. 3. Future directions for commercial adoption. Technological advancements, hybrid construction, integrate 3D printing with robotics and prefab for multi-story buildings. Smart materials, develop self-healing concrete and carbon-capturing composites. AI integration, use machine learning for real-time defect detection and adaptive printing. Market expansion, disaster relief, rapid deployment of shelters in crisis zones, e.g., Icons Operation Phoenix. Luxury customization, high-end architectural projects with bespoke designs, e.g., Dubai's Twisting Towers. Infrastructure, bridges, tunnels, and roads using large-scale printers, e.g., China's 3D printed pedestrian bridges. Sustainability goals, circular economy, closed-loop material recycling, e.g., WASP's Tekla. Net zero buildings, solar integrated facades and energy-efficient designs. Policy and industry shifts, standardized codes, develop global standards, e.g., ASTM/ISO, for 3D printed structures. Workforce training, invest in upskilling programs for additive manufacturing roles. 4. Conclusion: commercial 3D printing in construction is transitioning from niche pilots to scalable solutions, driven by cost efficiency, sustainability, and design innovation. Success hinges on overcoming material and regulatory challenges while fostering collaboration across industries. The future promises expanded applications in housing, infrastructure, and disaster resilience, positioning 3D printing as a cornerstone of modern construction. Key takeaways: prioritize material R&D and stakeholder collaboration. Balance innovation with regulatory compliance and public trust. Leverage hybrid techniques to bridge traditional and additive methods. Figures/tables, 1 table, cost/benefit analysis of select commercial projects. 2 infographic, timeline of major 3D printed commercial projects, 2016-2023. 3 case study snapshot, technical specs and outcomes for Dubai's Office of the Future. References: Dubai Future Foundation. 2016, Office of the Future Case Study. Icon. 2023, Community First. Village Impact Report. MX3D. 2021, Smart Bridge, From Concept to Reality. This chapter illustrates how commercial 3D printing is reshaping construction, offering actionable insights for industry leaders and policymakers to harness its transformative potential. Chapter 23, Research and Development in 3D Printing for Construction 1. Key research institutions and collaborations: leading academic institutions, ETH Zurich, Switzerland, DFAB House, a collaborative project integrating 3D printing with robotic prefab, demonstrating multi-story construction. NCCR Digital Fabrication, National Research Initiative exploring digital fabrication technologies. MIT, USA, Mediated Matter Group, pioneering research in bio-inspired materials and large-scale additive manufacturing. Project Olympus, developing lunar habitats using regolith-based 3D printing with NASA. 2 Delft, Netherlands, self-healing concrete, embedded bacteria to autonomously repair cracks. 3D concrete printing, 3D CP optimizing cementitious mixes for extrusion. Industry-academia partnerships, ICON and NASA, collaboration on Project Olympus for off-planet construction. Cobot and Perry Group, commercialization of the BOD2 printer for large-scale projects like Germany's first 3D printed apartment building. WASP and Rice House, sustainable housing using agricultural waste, rice husk, in Italy's Tekla Eco Habitat. Government and EU initiatives, Dubai's 3D printing strategy, aiming for 25% of new buildings to be 3D printed by 2030. EU Horizon 2020, funding projects like Beyond, hybrid concrete printing, and InnoChain, digital construction workflows. 2. Breakthroughs in material science and engineering: material innovations, concrete composites, Lafarge Holcim's Tector Print, customizable cement mix for high-speed extrusion. Carbon capturing concrete, CO2 absorbing materials, e.g., carbocrete. Alternative materials, clay and earth, WASP's Tekla House using local, zero-waste materials. Mycelium composites, bio-based materials for temporary structures. Smart materials, self-healing concrete, 2 Delft bacteria-activated crack repair. Phase change materials, PCMs for thermal regulation in printed walls. Engineering advancements, robotic systems, MX3DS metal bridge, robotic welding arms for structural steel printing. SciB construction, mobile printers for on-site flexibility. Multi-material printing, concrete insulation hybrids, layered printing for energy efficiency. Software tools, generative design, AI-driven topology optimization, e.g., Autodesk Fusion 360. 3. Future directions for academic and industrial research: technological frontiers, sustainability, circular materials, recycling demolition waste into printable aggregates. Bio-based binders, hempcrete and algae-derived polymers. AI and automation, real-time quality control, machine learning for defect detection. Autonomous swarm printing, coordinated drones/robots for large-scale projects. Space construction, lunar/Martian habitats, NASA's collaboration with ICON and AI Space Factory. Interdisciplinary collaboration, cross-sector partnerships, merging robotics, material science, and architecture. Global standards, developing ASTM/ISO codes for material testing and structural safety. Challenges to address, scalability, scaling printers for high-rise buildings and infrastructure. Cost reduction, lowering material and operational expenses for widespread adoption. Regulatory framework, aligning building codes with additive manufacturing innovations. 4. Conclusion: research and development in 3D printing for construction is accelerating, driven by academic ingenuity, industry collaboration, and governmental support. Breakthroughs in materials and robotics are paving the way for sustainable, scalable solutions, while future efforts must prioritize standardization, affordability, and interdisciplinary innovation. Key takeaways: collaboration is key, partnerships between academia, industry, and governments fuel progress. Sustainability first, bio-based and recycled materials are critical to reducing the carbon footprint. Think beyond Earth, extraterrestrial construction is no longer science fiction. Figures/table suggestions. 1. Table, major research institutions and their contributions. 2. Timeline, breakthroughs in 3D printing materials, 2010-2030. 3. Infographic, future vision for AI-driven autonomous construction. Reference, ETH Zurich. 2023, DFAB House, a case study in digital fabrication. 2. Delft. 2022, self-healing concrete, from lab to field. EU Horizon 2020. 2021, Beyond Project Final Report. This chapter highlights how R&D is transforming 3D printing from a niche technology into a cornerstone of modern construction, urging stakeholders to invest in sustainable, collaborative, and forward-thinking innovation. Chapter 24, Global Adoption of 3D Printing in Construction. 1. Regional variations in implementation. 3D printing adoption in construction varies globally, shaped by regional priorities, resources, and challenges. Middle East, Dubai, UAE, leadership, aims for 25% of new buildings to be 3D printed by 2030. Projects, Office of the Future, first 3D printed office, and luxury projects like Dubai Multi-Commodities Center, DMCC. Drivers, innovation-driven economy, government mandates, and tourism-focused architecture. North America, USA, affordable housing, Icons Community First. Village in Texas and Habitat for Humanity homes. Disaster relief, rapid deployment of shelters post-wildfires, e.g., California. Drivers, labor shortages, housing crises, and venture capital investment. Europe, Germany/Netherlands, sustainability, Perry Group's DFAB House and MX3DS Steel Bridge in Amsterdam. Policy, EU-funded initiatives like Horizon 2020 and Beyond Project. Drivers, green building goals and circular economy principles. Asia, China, infrastructure, 3D printed pedestrian bridges, Shanghai, and public amenities. Scale, Winston's 10-house project in 24 hours, 2014. Drivers, urbanization, government-backed tech innovation. India, affordable housing, T-Vasta's low-cost homes for the Housing for All initiative. Africa, Malawi/Kenya, 14TREES, affordable homes/schools using 3D printing to address housing deficits. Drivers, cost efficiency, rapid population growth, and NGO partnerships. 2. Policy incentives and market drivers. Policy incentives, government mandates, Dubai's 2030 strategy, India's national 3D printing policy. Subsidies and grants, EU's Horizon Europe funding, US Department of Energy grants for sustainable materials. Public-private partnerships, ICON's collaboration with NASA for lunar habitats. Market drivers, affordability, reducing costs for housing in high-demand regions, e.g., Malawi, India. Labor shortages, automating construction in aging economies, e.g., Japan, Germany. Sustainability, lowering waste, 30% reduction versus traditional methods, and carbon footprints. Disaster resilience, post-crisis rapid construction, e.g., Turkey earthquakes, California wildfires. 3. Barriers to widespread adoption. Economic barriers, high initial costs, printers, e.g., Cobalt BOD2 at $1m, and proprietary materials. ROI uncertainty, limited long-term data on durability and maintenance costs. Technical challenges, material limitations, anisotropic properties of printed concrete, lack of recyclable options. Scalability, printer mobility for large infrastructure, e.g., bridges, high-rises. Regulatory and cultural hurdles, outdated codes, most building standards, e.g., IBC, Eurocode, lack 3D printing provisions. Public skepticism, concerns over safety and aesthetics, e.g., layered textures. Workforce gaps, shortage of skilled operators and engineers. Logistical issues, infrastructure, transporting printers to remote areas, e.g., Sub-Saharan Africa. Supply chains, dependence on specialized material suppliers. 4. Future pathways for global adoption, standardization, develop ASTM/ISO codes for material testing and structural safety. Education, training programs, e.g., Zurich's MOS in digital fabrication. Hybrid models, combine 3D printing with conventional methods for phased adoption. 5. Conclusion. Global adoption of 3D printing in construction reflects regional needs. Innovation in Dubai, affordability in Africa, sustainability in Europe, but faces universal barriers like cost, regulation, and scalability. Addressing these challenges through policy alignment, R&D investment, and public engagement will determine its transformative potential. Key takeaways, regional strengths, tailor strategies to local priorities, e.g., disaster resilience versus luxury builds. Collaboration, cross-sector partnerships to drive standardization and skill development. Sustainability, prioritize circular materials and energy-efficient designs. Figures/tables, 1 map, global hotspots for 3D printing adoption, Dubai, USA, EU, China, Africa. 2 table, regional comparison of drivers, policies, and barriers. 3 infographic, policy frameworks accelerating adoption, e.g., Dubai versus EU versus India. References, Dubai 3D Printing Strategy, 2023. EU Horizon Europe, 2023. Beyond Project Report. 14TREES. 2022, Affordable Housing in Malawi Case Study. This chapter underscores that while 3D printing's global footprint is expanding, its success hinges on addressing economic, technical, and cultural gaps through coordinated efforts. Appendices. Appendix A, Glossary of Terms, Additive Manufacturing, AMA process of creating objects by adding material layer by layer, synonymous with 3D printing. Extrusion, a method where material is pushed through a nozzle to form layers. Topology optimization, computational design technique to optimize material distribution for performance and weight reduction. Generative design, algorithm-driven design that explores multiple solutions based on constraints. Geopolymer, a sustainable binder alternative to traditional cement, often used in 3D printing. Curing time, duration required for printed material, e.g., concrete, to achieve desired strength. Layer adhesion, bonding strength between successive printed layers. Appendix B, 3D printing equipment and material supplier, printer manufacturers, COBOD, known for the BOD2 modular printer for large-scale construction. Icon, Vulcan series for affordable housing, collaborates with NASA. WASP, crane printers for clay and sustainable materials. Material suppliers, Lafarge Holcim, Tector print cement for high-speed extrusion. BASF, advanced polymers and composites. Carbocrete, carbon-negative concrete alternatives. Appendix C, standards and guidelines, ASTM International, ASTM F42, standards for additive manufacturing processes. ASTM C39, compressive strength testing for concrete. ISO/ASTM 52900, terminology framework for AM. Dubai Municipality, 3D printing strategy, 2023, mandating 25% adoption by 2030. EU Horizon Europe, funding for sustainable construction projects, e.g., Beyond. Appendix D, design and simulation tools, design software, Rhino and Grasshopper, parametric design for complex geometries. Autodesk Fusion 360, generative design and CAD integration. Simulation tools, ANSI, structural and thermal analysis. COMSOL Multiphysics, multiphysics simulation for material behavior. Open source, free CAD, modular parametric modeling. Appendix E, additional resources, books, 3D printing in construction by A. Ballard, 2022. Additive manufacturing for the architecture industry, Springer, 2021. Journals, Additive Manufacturing, Elsevier. Automation in Construction *, Elsevier. Websites, 3D Printing Industry, www.3dprintingindustry.com. MIT's Mediated Matter Group, mediatedmatter.group. Conferences, Rapid.Tech 3D, Germany. Construct 3D, USA. Notes, formatting, entries are categorized for clarity, with brief descriptions. Currency, standards and tools reflect 2023 updates, suppliers verified for active status. Accessibility, glossary avoids jargon, resources include open access and premium options. This structured approach ensures each appendix is concise, relevant, and complementary to the main text, aiding readers in further exploration and application of 3D printing in construction. Conclusion: the journey through 3D printing of construction materials for rapid and cost-effective building reveals a future where imagination and infrastructure coexist. We've explored how cement-based mixes and sustainable geopolymers are extruded into habitable homes, how robotic systems assemble bridges with pixel-perfect accuracy, and how hybrid methods blend tradition with innovation. Case studies from Dutch canal houses to disaster relief shelters in Kenya illustrate a global shift toward agile, eco-conscious construction. Yet challenges linger. Material limitations, regulatory gaps, and public skepticism remind us that adoption requires more than technical prowess. It demands collaboration across industries and cultures. As AI and machine learning refine printing algorithms, and circular economies prioritize waste-to-wall solutions, the path forward hinges on education, investment, and inclusivity. The promise of 3D printing lies not just in its ability to erect walls, but to dismantle barriers, between cost and quality, speed and sustainability, today's needs and tomorrow's aspirations. As we close this book, let it serve as both a manual and a manifesto, a call to reimagine construction not as a relic of the past, but as a frontier of possibility. The blueprint for the future is here, layer by layer. This introduction and conclusion frame 3D printing as a transformative force, aligning with the book's technical depth while inspiring readers to engage with its visionary potential.